Hello and welcome to RF Design Tutorials, a playlist where we talk about practical RF and microwave circuit design. This is tutorial 6, and in this tutorial we will go over Smith chart and impedance matching fundamentals. Now, as you understand, impedance matching is a very broad ranging topic and there are plenty of things to talk about. Hence, I decided to cover the whole topic into a series of 3 tutorial video. So currently we are in tutorial 6 and these are the topics which we will discuss, starting from Smith chart basics going all the way to component tolerance analysis for matching networks. And we do have a topic to talk about broadband matching. Now in tutorial 7, we will extend our learning a little more about broadband matching, and we will be using an vendor provided S2P file, which is available on website. Then you would be able to use your own S2P file to try out input as well as output broadband matching under a single simulation. And also then we will extend our learning for doing multi-stage broadband matching. There are plenty of tips and tricks to go over during that topic. And finally, in the part 3, which is tutorial 8 of impedance matching, we will look at distributed matching networks. And then we will try to implement that matching network using microstrip lines, and then finally perform an electromagnetic analysis and verify the performance of our distributed matching network. So as you can see, plenty of topics to talk about, and it will take quite a bit of time. So let's get started. Now, before we start, you subscribe to my channel. And once you subscribe, click on the bell icon to enable all the notification. Don't forget to hit the like button if you enjoy the video, and click share to share it with your friends and colleagues who may be interested in watching a similar tutorial. Now let's first go and talk about Smith chart basics. And this is the regular paper Smith chart we are all aware of as electrical or electronics engineers. And on this Smith chart, some of the key points I mentioned here and some of the highlighted items would be something always good to keep in mind. Number one, a Smith chart is a polar chart representing complex impedance or admittance. And depending upon what we are plotting, we either have a Z Smith chart where we do see constant impedance, constant reactance kind of lines, or we can have Y Smith chart, or what we call as admittance Smith chart. And there we will have constant conductance and constant susceptance circle. Or we may have a combo Smith chart, which is ZY Smith chart, and we can have both of it. And for all practical purposes, having combo Smith chart actually simplifies a lot of our work. And we will see that as we go along, talking about various use cases. Now, Smith chart, you have a center line, which is basically called as a resistive line, where we have a pure resistance. And on one end, you have an open circuit where you have a very high impedance. On the left hand side, you have a zero resistance, and that's where we have a short circuit. The top half is inductive, bottom half is capacitive. So these are all, some of the basic fundamentals, which I assume you already know about, but just good to sync up on some of these fundamentals. One complete round around a Smith chart is equal to the half wavelength. That means if you make your transition from open circuit to short circuit on these two extreme ends, that's actually a quarter wavelength. And when you complete the whole circle back, you have the half wavelength, travel. Now, it also comes in very handy in many of the impedance network design aspects. So it's good to remember always. Now, to design your matching network, you could either use RLC or transmission line based components. And this tool is pretty universal, allows you to do anything you want in whichever implementation format you may want to work with. Now, the main limiting factor of a Smith chart in a classical Smith chart, you could only operate it on a single frequency at a time to design your impedance matching network, because all the values you calculate, all the impedance transformations you do ultimately will have to be scaled as per the frequency of operation. So you could typically can have only one frequency at a time. Well, that was your quick bit on Smith chart basics, and I hope you had a good time revising some of these fundamentals if you forgot for some time. Now, let's get started with other topics in this tutorial. So we just covered Smith chart basics, and now we will go over and look at different type of impedance matching networks, which we might end up designing due to different natures of different circuits we might be designing. And then for the broadband matching, we will talk about Q circles, how broadband is different than doing a narrowband matching network, and finally finish it off with doing a component tolerance analysis for our impedance matching network to see its sensitivity around the tolerances and component. Now for all this tutorial, I would be using Keysight ADS software, and if you already have ADS license, you should be able to follow what I'm showing you here directly. And if you don't have ADS license, you can always go to keysight.com, look for ADS and apply for the evaluation license to try some of these things out. If not, you could just follow the software you might be using at your side just to make sure you pick up the techniques from here and apply it as per the specific software you may have at your place. Right, to start with Smith chart, base matching network design in ADS, if you go to tools, Smith chart, and here you have a GUI, driven Smith chart, and here it's kind of different than this regular Smith chart in the sense there you only apply the transformation and then you have to manually calculate all the inductance, capacitance, or transmission line parameter. Whereas in this utility, it will directly give you this answer. So that's why I love working with these CAD tools because they make our job much easier and not go through the math theory of mathematics and apply various formulas and so on. But having those fundamentals is very important as an engineer so that you know what to do with this CAD tool. Right, in this Smith chart, as a normal convention, Smith charts are always normalized. So this Smith chart utility also comes up default as normalized. And the impedance you can set here as your characteristic impedance. And the center point here basically represent this characteristic impedance. However, if you have to unnormalize this, you can feel free to unnormalize it. And now this point will represent the characteristic impedance you are looking for. Now, before you go and venture into any kind of impedance matching network design, it's always a good idea to set up the frequency at which you are going to work. Now in ADS test bench here, I have plenty of placeholders, as you can see, for different conditions. And I have set up a sweep from 4 to 6 gigahertz. The reason for that is I would like to do my matching network design on 5 gigahertz for demonstration purpose. But depending on your application, you may be doing 400 megahertz, 800 megahertz, 2.4 gigahertz. You can feel free to use this utility as per that. Now in this Smith chart utility, you see there are two items at the center by default. And if I move them around, the circle represents basically the source impedance, and you can go ahead and place it wherever you want on a Smith chart. And this diamond shape of polygon represents the load, terminal. And again, you can feel free to place it anywhere. Now, because we have unnormalized our Smith chart already, and if we look, we can look on this node, it shows you the impedance as well as the admittance on that particular point. And similarly, you can click here. Now, sometimes people get confused by looking at these lines because they look far lesser number of lines compared to what you are used to see in a common Smith chart. And the reason that is, just for viewing pleasure, we don't want to have too complex line, interface with plenty of lines here. But be rest assured, the entire space in the Smith chart is usable by us, and we can place our source and load at any location, and we can find out the impedance. Or the other way to specify these impedances is by clicking on these nodes. As you can see, I can select the load and I can enter the impedance required for the load, and this point will shift to that particular point. For example, here in source, if I enter 50, what you will notice if I click anywhere, now this point will shift back to the 50 ohm point or the unity point. Now this is how the typical GUI looks like. Now the reason we come up with C Smith chart as default because this option is selected. If you click on this option, including the first option, now you have a CY Smith chart. And if you disable the Z Smith chart, you only have the Y Smith chart. So again, depending upon what kind of matching network you want, what is your preference, you can set the units accordingly or the mode of the Smith chart accordingly. Also, using this button, you should be able to switch on and switch off whatever circles you want to see. So currently is C Smith chart. You can see R and X, and if I disable X, I only see constant resistance circle. Similarly, if I switch off everything and I just want to see constant conductance circle, this is how you can enable. So again, this can be customized based on what you need. Now here, let's go and get started with our first matching network. And the first matching network I would like to do is to match a 50 ohm source with a complex load. And the complex load I want to match is 5 minus J5. Now I just picked it up based on my convenience. In real life, this could be your antenna input impedance, which you want to connect to a 50 ohm, and you want to design a matching network to match antenna. Or if you're a circuit designer, this could be BJT or FET's, input impedance, which you want to match. So instead of connecting an S parameter file or S1P file of antenna or a measured file, I just, for the sake of simplicity, I put a termination and I define the complex impedance which I want my matching network to be designed for, and the matching network will be get placed here. So in order to use the Smith chart utility and whatever network we will end up creating here based on our source and load condition, we would like that schematic to get populated here. And the way we do that by clicking on this pellet icon here. Once we click on pellet, so let me change this behavior. Let's say you are in any other library in ADS. And now if I click on this pellet icon, it shows you the Smith chart component. And this is what we call a smart component. We can pick this and we can place it anywhere in our design. Now this component by default has a 2 terminal. The input terminal is denoted by this hash line. Like any other component in ADS, you can see the cross line in every component. So this is basically the source impedance point, and that's the load impedance terminal as per the GUI. Now, in order to get started with our first design, I would set source to 50 and load, as you can see, ZL, and I need 5 minus J5. So let's go ahead and enter 5 minus J5 and click anywhere. And now we can see our load point gets shifted to the desired location. Now, once I have source and load in place, I can go ahead and lock it so that accidentally I don't change these points. And once they are locked, if you try to move it, ADS will prompt you that it is locked. It cannot be modified. So you can unlock it if you want to modify it. Anyway, so those are some fundamentals. Now, to do impedance matching, basically we just need to find a traveling path between source and destination. And the way we can make this journey is by using these components which you see in the pellet. You have inductors, capacitors, resistors, transmission line, and transformer. Now using some of these components and the way you connect them, your impedance will get transformed from one place to another. And that's what we will learn in this tutorial plenty of times. Right, so if I add a series inductor, you notice what happens when I move my mouse in the GUI. I have trajectory of my impedance based on the inductance value, and more distance I cover from the load point, I have higher value of inductance. But if I cross this infinite impedance point and I come to capacitive plane, my inductor will turn negative, as you can read in the right hand side on the left top side here. So I need to be within inductive zone. Now to make my journey smoother, I can switch on the Y Smith chart, and now I can see constant conductance circle, and I know this is the unity conductance circle, so I can place by clicking on a particular point, it inserts that component, and here's our network which we are building. And this inductance, if I click on that, it shows you the value 642 picohenry right now on 5 gigahertz. Right now, in order to at the same time while we are designing network, I also want to see my frequency response. So I can quickly set up this plot here. And let me go ahead and set it to 6 gigahertz as a stop frequency. and start frequency as 4 gigahertz. And now this sets my x-axis. For y-axis, I can select the kind of format I want to have. So dB, and then I can set max and min. So 0 to -50 is kind of sufficient for me to see the entire matching network response. Okay, coming back to our matching network. So with one component in place with a specific value, I have this component place. Now, in case I want to change this point to some other location, I could either pick this green dot and I can move it around a Smith chart. And once I do that, you can see the value changes. Now, another way of doing that is modifying the value here. So in this case, if I apply 2000 picohenry or 2 nanohenry, and if I press enter, you can see the load point shifts at that location. So it's very flexible utility, very easy to use, and it makes your impedance matching job, a piece of cake in a way. Right, so once we reach up to this point, I can stop. And now I need to travel through from this point all the way to unity point. And now we all know that if we add a series capacitor, and you can make your journey, right? No. Right, so every component which you add will have a certain trajectory. You can see series capacitor is a phase opposite component of series inductor. So while series inductor was taking you in a clockwise direction on the inductive side, series capacitor will take you counterclockwise in the capacitive side. So even if sometimes you get confused which component to use, and you can feel free to try. Nothing goes in trying. And if you find series capacitor is not taking you to the right direction, you can try with shunt capacitor. And now definitely you can see your locus is moving towards the right direction. And once you hit the unity point or 50 ohm point, you click. And now you have the frequency response and you have a nice LC network for you to use. And now this capacitor value, if I click here, it's 1.9 picofarad. And if I click here, it's 635 picohenry, which seems to be okay. Now I want to take this result back into my schematic, and ideally what I should have done before starting this design, you see there's a placeholder, and now if I select match 1, which is the name of this component here, I could have synced this component with this utility. Let's do it now. It's never too late. So once I select match 1, ADS asks you what format would you like. So I would like to update the component, this component from my utility, because I already have done all the changes. Okay, so now if I build up this circuit here, and if I push inside, that's the network which we just created in a Smith chart. So now all in all, I have my circuit and I already have two terminations, 1 and 2, connected across this network, and I already have a controller for my simulation. I can go ahead and run simulation, and I should be able to plot S11 or S22 to look at the matching performance. So here, if I plot S11, I can notice a nice, kind of resonance match at 5 gigahertz. But of course, this is a narrow band match, but it has done its job, what we were expecting for it to do, and which is matching at 5 gigahertz. Now, if we go back, let's talk about one practical consideration which sometimes people forget. I want to make sure I cover that. And that is, let me switch off this Y Smith chart first. So all these components in reality will have a finite Q factor, which is their quality factor. So inductors on such high frequency will not have a very high Q factor, and that will affect the quality of your match network and also will associate certain loss in the component, and which eventually will become insertion loss of your matching network. So in order to allow for more practical modeling, when you add these components, you could also invoke the loss and enter the Q factor. And you can see by default, it has a very high Q factor, which makes it like an idealistic non-lossy component. So here, let me enter the quality factor of 20, which is very typical at 5 gigahertz for a discrete inductor. And when I click here, you can see the matching gets disturbed now, because now you have a finite loss or a resistance inside this pure reactive component. Similarly, for capacitors, we can include the loss, But luckily, capacitors typically have a very high Q. So if you enter 500, which is very typical for capacitor at 5 gigahertz of this low value, and if I click anywhere, we can see there is no major change in my network. So now in order to compensate for the Q factor, I can pick this green point and I can compensate it by increasing the inductance value a little bit. And then finally, because inductance is getting increased, capacitance has to reduce. So we can go ahead and reduce this capacitance a little bit. And now we have a compensated, kind of circuit response. So we'll go ahead and build ADS circuit. So the previous circuit which we built will get overwritten. And now you can see you have new components with proper Q factor assigned. And now if we go ahead and run a simulation, now we have a response with components including the Q factor. All right, so that was a good tip to remember whenever you guys deal with, doing this kind of matching network. Now let's talk about the second case. And in this case, we have a complex source to match with a 50 ohm load. Now think it like, output stage of your amplifier, and this could be the output impedance shown to you by a BJT, FET, or whatever. Or this could be a receiver application case where this could be impedance of your receiver antenna, and you want to match it with a perfect 50 ohm isolator or a filter or any of those components. So again, but the point here is my source is not 50 ohm like earlier. My source is a complex impedance and my load is 50. And one might ask, what's so great, about it, because it looks like pretty similar case. Yeah, it's pretty similar. However, there's a subtle difference between how we did that and how we are going to do this. Let's see. And now we can insert a new Smith chart component to reflect match 2. And once we go back to the utility, and now we are going to, invoke match 2 so that it gets linked up with our utility. And once we have the sync, now we can go ahead and, create a new Smith chart by clicking on this icon. It flushes out all the data we have, but it still retain all the other key parameter. So in our case, we have Z load, which is 50, and we know that. So let's log the load. Now source is 10 minus J5 as we need here. In this utility, as you can see, it's recommending to enter the complex conjugate with this asterisk sign. That's what this means in RF microwave. So we'll go ahead and enter complex conjugate of what we need. So we need 10 minus J5. So we will enter 10 plus J5. And now we can notice this is the point, complex conjugate. Otherwise, if you plot 10 minus J5, it will be somewhere here. But now it's complex conjugate, which we need to match. So that's it. So once we log the source, again, the same process we can employ. Remember the direction or the trajectory will always, or the traveling will always start from the load side. So now you will start from the unity circle and you will move towards the source. So if we add a shunt inductor, you can see we have the right trajectory. And if you accidentally pick the wrong component, you can very visually see you are going in a wrong direction. So, but again, to do impedance matching, you have various ways. So you can do a low pass kind of matching. You could do a high pass. For example, to reach from, this point to that point, you could go down with a shunt capacitor, for example, and from here to move up in a clockwise direction, you can just employ a series inductor. And once you do that, look at the resulting circuit. It's like a low pass topology, like we obtained earlier. The another way to do the same thing is using high pass topology. And when you click on shunt inductor, you can see you are moving in this direction. And I can stop at this constant resistance circle of 0.2. And then if I add a series capacitor, I would move in this direction. And now we have the same matching network, but with a high pass topology. Now, another practical question with a lot of people ask is, which one should I prefer? Is high pass topology better, or is low pass topology better? Well, it depends on the circuit, number one, how far you are and whatever is the most convenient way to reach to that point. Secondly, you should also look at, for example, if I go with high pass topology, the shunt inductor I need is like 0.7 nanohenry. and the series capacitor ID it is around 2 picofarad. Now if you already have it in your inventory, probably you might want to go with this topology, or if you try some other topology you may come up with a different values for this matching network. So again, choice is yours, and sometimes you don't want to do this two element matching. Let's say I still want to have this topology, but I want to have at least two sections to increase the bandwidth a little bit or to have more tolerant circuit. Then instead of directly reaching to that point, I can stop somewhere here. For example, I can go only up to this point, stop at this location here, add another shunt component and I reach here, and add another series component and I reach here. So now I have two LC sections, two high pass sections here. So basically again, it's pretty dependent on what would you like to do. Now I can go ahead and build ADS circuit. It's referring to match 2. So let's go ahead and build ADS circuit. And now if you push in, you have the same topology. And again, if you would have invoked the quality factor in a Smith chart, you will have with Q factor here. But again, let's go ahead and quickly simulate it. And we already have one S11 plot. So we will do Control C, Control V to copy and paste, and then do a single click here and just modify this measurement to S33. And now we can look at S33 performance, which is again coming out to be very good. Now, so we just covered two cases. Now let's come to our third case where we want to do complex source to complex load matching. And let's insert another Smith chart component here. And the name of this component is match 3. So I want to match 10 minus J5 to 5 minus J5. Now, what is the practical use case here where you might see this scenario? Well, think about multi-stage amplifier design or multi-stage circuit design. This could be output impedance of the first stage at a specific frequency. This could be input impedance of the second stage at a specific frequency. And you would like to do this interstage matching network design. So let's see how do we handle that using a Smith chart utility here with basic fundamentals. So first thing I would do here is to update this component to match 3. And then it will ask for sync. That's okay. And now we have synced between this utility and that component. Let's go ahead and create a new matching network. Now load is 5 minus J5. I can enter directly 5 minus J5. Now the source as needed in our circuit is 10 minus J5. So we'll go ahead and enter complex conjugate of that. Always remember that. So 10 plus J5. And now I have my source and destination pretty much fixed up. Now, in order to make this journey, you have a couple of ways. Let's look at first way. So if I have to go from here to here, that can be very simply done by switching on a series inductor, reaching to a point, and then switching on a series capacitor, shunt capacitor. And now we can adjust this trajectory to intersect with the desired source point. And now once we go there, we can adjust this value. So simple LC network gave you the matching which you wanted. That's option number 1. Now, option number 2, sometimes some designers would always want to take this load point to the unity point, which is 50 ohm point, and then from there reach to this point. Again, that offers certain advantage and a little better match, but again, it depends on designer what they want to do. So let's see if we have to go to the unity point and encircle this unity point in our matching. So we could add a series capacitor, and you can see we can go down. And again, where to stop? We can switch on Y Smith chart. And now we know this is the conductance circle of 1. So we stop here. Now from here to here, we can simply add one shunt inductor. And now we can go to this point here. And now you can see you have LC and you reach to the unity point. Now from here to here in this direction, again, we can add a new shunt inductor if you want, or take the same shunt inductor and we just continue our journey till this point, because even if you have two parallel inductors, it doesn't make any sense because you can have a parallel inductance, which does exactly the same job. So once you reach here, now we just add one more series capacitor and you move here. So this way you get the same complex to complex impedance matching, but now you are encircling or going through the unity point, and this is your matching network, which is like a T network. Now we go ahead and build ADS circuit. Both approaches I showed here is fine. It depends on what you want to do. And once we simulate, we just copy paste Control C, Control V, and we plot S55, which is the input termination for our network, or if I can plot S66 is basically the same thing. And now you can notice in complex to complex case, again, you have a pretty good matching network response. All right, so hopefully you are getting sense of what we are doing, and we are almost halfway through. But I promise it would be, over in another 15 to 20 minutes maximum. So you are doing good job staying till this point. Few interesting topics coming your way, so stay tuned. Right, so let's now talk about broadband matching techniques. And there comes a concept called Q-circle. So let's understand what is that. Now in broadband impedance match, I have this condition here, and let me connect a Smith chart component. Now this is called match 4. Now just for example's sake, I have picked up source impedance as 50 ohm and a load impedance of 5 minus J5, which is exactly the same what we had here. But there we didn't care about the bandwidth. We just said, okay, we want to reach from here to here at 5 gigahertz. And we did one simple LC matching and we reach. Here, I would like to do a broadband impedance match. I would at least like to obtain 2 gigahertz wide bandwidth in this matching network between 4 to 6 gigahertz. Right. Now let's go back to Smith chart, switch it off. I'll switch to match 4, which is the new component I placed. And now let's start a new Smith chart. So the source is 50, load we need is 5 minus J multiplied by 5, which is same as before. Now when we want to do matching network for broadband frequency, here comes the concept of Q circle. And once we go to circles, we switch on Q, and now we can enter what's the Q factor we need. Now the formula for this Q factor is pretty simple. It's center frequency divided by bandwidth. Now the Q of 1 simply means your center frequency is equal to bandwidth, which we call as 1 octave bandwidth. That's the theoretical limit shown by this circle. Now, if you have higher Q number, that means your bandwidth will be lesser and lesser. And when you want to do narrow band impedance matching network design, basically you have access to entire Smith chart. You could do whatever you want. You could have any kind of network. However, broader the bandwidth you need, as you can see, lower will be the Q. And lower is the Q, lesser area you can utilize inside a Smith chart to do your impedance matching. So does that, raise some thinking caps on? All right, so Q factor of 1, okay, means I could only utilize this much area in a Smith chart. And if I have my impedances, which I want to match outside this Q circle, whenever we design you have a matching network, we first need to come in. So let's see how. So once we click the series inductor, I came inside. Now in the previous case, in the first case, I went around this point here, and I then added one shunt capacitor to reach here because I didn't care about the bandwidth, and you are free to do that. But you can see you're outside this Q circle, and that's not recommended. So you need to come back to Q circle here, and now we can add, shunt capacitor. And now you can see your selection gets very limited because now you are bounded by this Q circle here. You can't cross here. And once you keep drawing or keep matching, you keep designing a matching network. Basically what you're doing here, look under networks, you are creating this multi-stage filter kind of response, which is like a low pass filter. Okay, so now once we have enough sections, we should be able to reach our desired 50 ohm point, like in this case. And now with this 50 ohm point here, okay, we have wide enough frequency response seemingly, but we end up having these many components. So wider the bandwidth, more number of components you might end up needing. Now, I'm surprised nobody till now asked, Q factor formula which you told is center frequency divided by bandwidth. Isn't it the same formula which we refer in terms of filter? Yes, of course, it is filter because all matching networks, no matter what you do, is actually filters. They're simply impedance transforming filters which are working on unequal terminations on each side. Because if you had both 50-50 ohm each side, then you have no impedance matching concept anyway, right? So they are nothing but normal filters. We call them impedance transforming filters. So all the theory, all the thinking you need to do, just think it like a filter design, and you would be very, very comfortable with doing impedance matching network. All right. With this concept, I have my first cut broadband matching network. I go ahead and build ADS circuit. And if I push inside, I have this LC. But remember, right now, they are all ideal components with zero, resistive. And you can see resistance here is very small. That means Q factor is very, very high. But in the utility, as I showed you earlier, if you would have included Q factor, you will have a finite amount of loss. And that's one thing you need to deal with while dealing with broadband impedance matching. More number of section means more insertion loss. So if you're doing a LNA design and you are doing input matching, this will directly add up into your noise figure. If you're doing power amplifier design and if it is your output stage, this will directly eat up all your power, number one. Number two, all your components should be of that power handling capacity. That means you might need to end up buying a lot of high power components. Okay, we will talk about some of those once we go to those respective topics. But here coming back, I simulated the circuit and now I have this S11 and now I can double click, and one new trick you will learn here. I have tons of S parameter component and I just need to plot S77. Can I do that without going through and searching in this list? Of course you can. And the way you do that, in the search bar, just type 7,7 and now you have S77 and you can add it. And if you want to see the loss, just type S87 and now you have this S87 and you add. And now you can go ahead and look at the entire performance. Now notice the blue trace, which is representing our broadband match, has much wider bandwidth compared to what you used to have. Even if you look at 20 dB match is almost from 4.4 to 5.8, resulting in 1.4 gigahertz bandwidth. If you look at minus 10 dB bandwidth is more than 2 gigahertz, and if we do a wider sweep, you can see you will at least have like a 3 gigahertz kind of bandwidth available in that match. Now, some of you till now must be thinking, well, he's talking about a broadband match, but he's not talking about this impedance. How can this impedance be constant across the entire frequency band? And you are thinking correctly, my friend. And that's precisely the topic of our next tutorial, where we will use S parameter and we will talk about how to deal with this broadband impedance matching case when you have this impedance, which obviously will vary. And we will also talk about multi-stage matching, because there not only this impedance is varying with frequency, you also have this impedance varying with frequency. Then how do you go about doing impedance matching in network design? Right? So stay tuned for the next video. Now, if we go back to our agenda, we talk about almost everything. We talk about differences between narrowband and broadband. We talked about concept of Q circle. And finally, let's quickly talk about component tolerance. Because now I have a network where I have both narrowband as well as broadband. So let me copy paste this network here. And let me delete this red trace. So now I have two separate networks. And also I don't want to see the transmission response. So this is just a bare matching network performance. Now in real world, all the components which you have inside your network will have some tolerances, plus minus 5%, 10%, 2%, right? So our impedance matching network has to be tested with what will happen if there is a tolerance of certain percentage. So one of the previous videos on my YouTube channel, I talked about running Monte Carlo and yield analysis, and we are going to do the same thing here. So we go to Optim-STAT-DOE library, and just to show you something simple, I can place Monte Carlo and link our simulator. So put a couple, double quotes, SP1, which is name of our S parameter simulator, we placed on this schematic. And I'm going to run 250 iterations. And again, if you want to understand this in a deeper level, please go ahead and watch that tutorial. It's pretty much available on the same YouTube channel. So once I have SP1, now next thing I want to do is assign tolerance to these components. And we can go ahead and go to simulate, simulation variable setup. And then the statistics, you see you have all the components listed here. I'm going for all the matching networks here. So I'm going to enable the tolerances among all the components we have across all the matching networks here. And let's see which matching network perform better, which matching network perform worse, and things like that. So with few simple clicks, I could enable these components to have certain tolerance. Now these tolerances by default, ADS, as you can see, is a Gaussian distribution, plus minus, and if you calculate the number here, that's basically 5%. So ADS by default will assign plus minus 5%. However, if you want to change, go ahead and change it to 2% or 1%. And there are various formats you can define the tolerance. Right now I have used an absolute value concept here. All right, once all the components are enabled for tolerance, let's save it. And now let's run a simulation. Now ADS will run a statistic simulation in the background. And now you can notice all your circuits are changing. So let me delete these two wideband circuits from here. And now what you're only seeing is the response at 5 gigahertz of your narrow band. And you can see it is going as bad as, minus 10, or in some cases with a slight bandwidth even, worse than minus 10 dB. So it looks like pretty sensitive circuit. However, if we look here, although the resonant frequency is moving, but large part of this circuit is below minus 15 dB. So despite having so many tolerances and such a high number of components, you are still able to meet in a very broad band a return loss better than minus 15 dB, just out of the box. Now, using a statistical design techniques available in ADS, I could even further tighten this. I can center my design properly by running yield analysis, by running yield optimization, and so on. This is just something out of the box. And you can see all the main narrow band circuits, you have much worse performance than you expected. Right? And that goes on to prove the point that whenever you have an opportunity, don't restrict your matching networks just to a simple LC. As you understand, this has one resonant frequency, and slight tolerance in LNC will shift your resonant frequencies, right? So having somebody to absorb the variation, such as in this case, it will always going to give you a little more statistically robust design. But when possible, compromise again have to be made on bill of material, how much cost and how much area you have on your PCB or chip to go ahead with your matching network design. All right, so with this, we come to end of this tutorial. It was slightly long tutorial, and you could understand pretty much why. We had a lot of topics to cover in last few minutes, but I hope now you have a better understanding of some of the common things which you end up doing in an impedance matching network design. And if not everything was new to you, but at least one or two things new which you found in this video, which will be useful for your work. Now, thanks again for staying back till the end of the video. And I welcome you to have a look at tutorial 7 and 8 whenever it is available on my YouTube channel. And hopefully that will enhance your learning even further to look at some of the realistic practical test cases of doing impedance matching network design. All right, thanks a lot for your time. Don't forget to hit the like button and subscribe to my channel if you haven't done so already. Wish you all the best in your design work and have a great day ahead.